Chapter 3, Descriptive Measures for Populations and Samples, starting with Section 3.1, Measures of Center. The first type of measure of center that we're going to look at is called the mean. You've probably heard of the mean referred to as the average before. And we're going to look at two different types of means. If our data is population data, then we'll look at the population mean. If we just have sample data, then we'll calculate a sample mean. So population mean, or average, and we use the symbol mu for that. It's the Greek letter, kind of looks like an M, kind of looks like a U. It's mu. But the way we calculate a mean is just like we've always calculated an average. We take the sum of all of our data, or add it up, and then we divide by the total number of pieces of data that we had. And a little bit of notation that goes with that. We have the capital Greek letter sigma, and we use that to mean that we're taking the sum. And then we have the variable x, which just represents our data, so the sum of our data, and then dividing by the number of pieces of data. We're using a capital N to signify that it's the population mean, because capital N stands for the population size. We basically do the same math if it's a sample mean. It's just different because of the type of data, and we want to distinguish that with our symbol. So instead of using the mu, we use an x with a bar over the top of it, and we have the clever name x bar for that. In symbols, what we do is add up all the data values again and then divide by the number of data values. But because we're talking about sample data, we're going to divide by the sample size, and we use a little n for that. Now, because these means involve division, a lot of times we're going to get repeating decimals, so we'll want to round those. And our rule for that is going to be always round means to at least one more decimal place than the original data. So if the original data was whole numbers, go one decimal place. If the original data had 3 decimal places in it, then put 4 decimal places when you calculate your mean. So let's look at a quick example. Suppose this is the amount of money in dollars that 9 friends of a study group have on them to purchase lunch. Find the mean, and assume we're only wishing to describe the center for these 9 people. Alright, so here's our 9 friends. They have $4, $12, $18, $10, $13, $6, $7, $0, maybe the most realistic number in the group, and then somebody brought 55, and they want us to calculate the mean. And they say that we're only wishing to describe the center for these people, so that means these people are the population of interest, so it's going to be a population mean that we compute. So I'm going to use the symbol mu. I'm going to want to find the sum of those x's, and then divide that by the size of my population, which is 9. And let's go ahead and find that sum. So bring in the calculator. And just add those up real quick. So 4 plus 12 plus 18 and so on. So when I do that, I get $125 altogether. So that's going to be my numerator. So this mean becomes 125 divided by the number of people that are in our population, which is 9. So now we want to go ahead and do that division. So that 125 divided by 9 gives us approximately, and then it's 13.8 repeating. So according to our rounding rule up here, we need to use at least 1 decimal more than the original data. The original data was whole numbers, so we have to go at least 1 decimal place. The phrase "at least" does give us permission to go further than that if we want, and because this represents money, I think it would make sense to go 2 decimals instead of just 1. So I'll go ahead and remind myself that it is money, put that $sign there, and then say that my average is about $13.89. So that should be a calculation you've done before, calculating the average, but we do have some new things to think about. The first question is, do we have a population or a sample? This was a population, so I used the symbol mu, and then thinking about some rounding issues that maybe we didn't have before. Alright, now that we've computed this mean, I think it makes sense to pause for a moment and think about why did we do it and what is it good for? And to be honest with you, in this particular situation, I don't know if it is a lot of use. A lot of times I'll ask students, what could this group do with this mean? How is it useful to them? And I'll hear answers like, well, that tells them how much each one of them can spend on lunch. And there is an interpretation of the mean where that would be a good answer. The mean is sometimes referred to as the fair share value. If you were to take the total and distribute it evenly to all the people in the group, this is how much money each one would get. I don't know what it's like with your group of friends, but usually when I go out with people, we don't just take all of our money and throw it into a big bucket and share it. So unless this person with the 55 and some of those other folks are willing to throw all that money together, I don't know that this number is going to really come into play. Another thing that sometimes people will think of for the average is, well, it is a measure of center, right? So it probably at least tells people in the group if they're in the top half of the money holders or the bottom half. But it turns out that in this group, it doesn't do that either. If this really split the group in half, then you'd probably think like that one of these people would be at this value and 4 of them would be above and 4 would be below. But if you count up how many of the people out of these 9 are above average with their money holding, you only have 1, 2, and it looks like that's it, right? So out of 9 people in the group, only 2 of them have an amount of money that's above average. So that interpretation kind of falls short here too, that this idea that the mean would split the data set into 2 halves, like a top half and a bottom half. And that actually is something that we really do want. So we're going to go ahead and move on and define a new term called the median that serves that role of giving us a top half and a bottom half. And we'll return later to see some uses for the average, but it turns out that the average usually is most useful if the total of the data is somehow important. All right, so let's go ahead and move on to this median. So the median is only taken of an ordered list. So we'll go ahead and make that note first of all. And then when you're looking for the median, you are looking for a value that kind of splits the data set into 2 halves. And whether you can do that or not depends on if you have an odd number of values in the list or an even. So we say the data value is the value that's exactly in the middle of the data set, but you can only do that if the number of items is odd. So what do you do if it's even? Well, if there's an even amount of data values, there'd be in a sense 2 middle values, and so what we do is we take the mean of the 2 middle values if the number of items is even. So we'll start out looking at the example of these 9 friends in their study group and the amount of money they had, and then we'll move on to an even list later to see how that second part of the definition works. Sometimes when you're going to find a median, you have really big data sets where it's hard to see the middle by eye. So we do have a formula for helping us find that. And I'll show you that in just a moment right here. But first I want to just go ahead and try and find the median of this set by eye because I think that's a little more intuitive, and then we'll come back to the formula. So looking at our definition, medians are taken of ordered lists, and this list is not in order. So we do want to go ahead and put it in order from smallest to largest. So that looks like that would be 0, 4, 6, 7. Go ahead and kind of keep track of the ones we've dealt with there. Now it looks like it would go 10, 12, 13, so 10, 12, 13, and then we still have the 18 and the 55. So now that's in order, and the median would be whatever value in that list is in the middle, and just kind of looking at it by eye, it looks to me like that would be this one. Sometimes I do get an answer 13 from people and I ask them about that right away, which indicates they forgot to put it in order. So always put that data set in order before you would try and find a median. All right, let me go ahead and show you how this location formula works. And again, I don't think you'd want to use it here. It's kind of overkill. But what you do is you take 1/2 times the number of data values, and that'll tell you the location in the ordered list where you could find the median. So I go ahead and leave that like that. There's our formula. But if we were going to apply that down here on this one, we could say that the location of the median was 1/2 times 9 data values plus 1. So that's 1/2 of 10, which is 5. It's important to notice that 5 is not the median. 5 is just where the median is located. 1, 2, 3, 4, 5 spots into our data set is the median of that data set. And I should label this too. This is a capital M is what we usually use for the median. So the median of our data set was $10. And again, that's not necessarily useful for this group in terms of buying lunch, but it does at least tell somebody if they had $6, they're in the bottom half of the group. And it now correctly tells the person with $13 that they're in the top half of the group because it's above the median of 10. Whereas when they were looking at the average, they would have thought because they had a below average, they were in the bottom half, but it's really not true. they're up there in the top third, but they're still below average. So if you want to know top half, bottom half, the median is the one that you would use. A quick note on this formula: if you had sample data, you would use a little n, a lowercase n, instead of the capital. All right, let's go ahead and look at one more thing with this, and that is what would happen to these two answers if the person who brought $55 had instead brought $555. So let me just throw an extra 5 on there. And actually, I guess it'd be thrown out front, right? $500 bills thrown into this total, and now they have 555. So what does it do to our two answers? Let's start with the median, because that's the easiest. The median is the number in the middle, and when the person with the most money all of a sudden has more money, that doesn't change the situation for the middle person. So the median would still be $10. The mean, on the other hand, does change. Now, when we throw all of this money into the bucket, this person has $500 extra, so instead of us having a total of $125, we would have a total of $625. There's still 9 people, so we take that 625 and divide by 9, and that would give us our new population mean. And if we still stick with that idea that it's money, so let's go 4 decimal places, that'd be $69.44. So if indeed they were going to throw all this money together and share it, and everybody got to spend this amount for lunch, then that's good news for 8 people in the group, because all of a sudden they get to have a much nicer lunch than they brought money for. And this person might be surprised to learn that and might not think of it as such a fair share, but that's what it would be. If we threw the total together and split it up, it'd be about $69.44 each. And I do think it's interesting to note that when we make that change where this person has that $500 extra, now all of a sudden the person with $18 who brought the second most money from everyone in the group is actually still below average, and only the one person with the $555 is above average. So you might be surprised to see that the average really doesn't split things necessarily into a top half, bottom half. Sometimes it does, sometimes it doesn't, and we'll kind of see some of the rules for when that happens, when it doesn't happen, as we move through the section. All right, moving on to page 2. While we're talking about measures of center, I'm going to throw one more in there with the mean and the median, and this one's referred to as the mode. The mode is the data value or values that occur most frequently in our data set. If there's no repeats, then there's no mode. Some special names: if we have a two-way tie for the most repeated, we'd have 2 modes and call it bimodal. If there was a 3-way tie for the most repeated data value, then we'd have 3 modes, and it would be referred to as trimodal. You don't have to memorize those special names, but you may see them from time to time. All right, so the mode is the data value or values that occurs most frequently. So we're going to go ahead and move on to a new example here and look at the mean, median, and mode, and continue to talk about how those are used and calculated. So an intermediate algebra class completed a chapter quiz using an online homework system. The time in minutes spent by each in a random sample of 18 students on the assignment is shown below, and we wish to use that to make estimates about the entire class. So the first thing that is worth pointing out is this a sample or is it a population? And we've got that clearly stated for us here. This is a random sample of 18 students. And then we see that it really is a sample because they don't wish to just talk about them, but they want to make estimates about the entire class from this part of the class that they collected data from. So just make a quick note of that for later. This is sample data. So when we make that decision about is this a sample mean or a population mean, now we know it's going to be a sample mean. So they want us to calculate the mean for the data set. That's going to involve adding all the data up. They want us to calculate the median of the data set, and that's going to involve putting the data in order. And both of those two tasks can be made a little bit easier if we bring in technology to help us. So I'm going to show you how that works. So I'm going to go to the calculator, and I'm going to enter all this data in. And the pathway to do that is using the Stat menu. So I'm going to hit the Stat menu, and then I want to edit some data, enter some data really, but I choose the Edit menu to make that happen, and it's already highlighted. So I just press Enter, and then enter these in. It doesn't really matter if you go down or across. I'm going to go down. It's a little easier for me to track it that way, but as long as you get all the data values in, that's all that's really important. After each data value, I'm just pressing enter. You can also press the down arrow key after each one, and that has the same effect. Alright, later on in this section we'll find out that our calculator can do some really powerful stuff with that data. For now, I just want to have it help us in the process of doing the sum and putting the data in order. So I'm going to go ahead and move it out of the way for a second, and let's get started on the calculation. We'll bring the calculator back in and out as needed. So when we go to do the mean for the data set, notice it just says the mean. There really is no such thing as the mean. There's different kinds. Right now we know of two kinds, the sample mean and the population mean. Since we've established this as sample data, they must mean the sample mean. So I'm not going to use the symbol mu this time, I'm going to use the symbol x bar. And I'm going to want to add up all that data, so the sum of the x's, and divide it by the sample size, that lowercase n. Okay, at this point the calculator can come in handy again. I've got all that data put in there, and I can use the calculator to help me get the sum. I don't want that sum to be stored in the same list as my data, so I'm just going to use the arrow key to move over into the square, and I'm going to have the calculator store the sum there. That way I can kind of just stay in the same place as my data. And to get that sum, we want to use the list menu. The list menu is right above the stat key. So I'm going to hit second and list. Then I want to do some math. And the math I want right now is the sum. I'll go ahead and point out it can do the whole mean for us, but we'll get to that later. Right now I want to just go ahead and still do the work in a way myself, but use the calculator to make it a little less tedious. So I'm going to pick the sum, and then what I want is the sum of L1. So notice right here it's asking me, what do you want the sum of? Down here at the bottom of the calculator above the 1 key it says L1. So if I hit second and L1, then now I'm telling the calculator I want the sum of L1 right there. So when I do that and press enter, I find out that the total is 632. So I move this out of the way again. So we have 632, and then divided by the size of our sample, which was 18. And then we're going to want to go ahead and get the mean. And as I bring the calculator in, just a couple other things to show. We know that our sample size is 18. If we go down to the last value in our list, 46, then if we look on the calculator, we can see down here that it's saying that in list 1, the 18th value is 46. It is sometimes good just to make sure your last value has that number that matches your sample size so that you didn't miss anything or get anything extra times. Okay, so let's go ahead and do that division. So we already have that answer. I'll just go below that here. So we want 632 and then divided by 18. I already put approximately equal to, assuming this is going to come out messy, but which it probably will, but let's see. Yeah, 35.111. It looks like it's a repeating decimal. When you use this little column area as kind of like a scratchwork area, you don't get to see a lot of the decimal places on the number. If you use the arrows to highlight that, you can actually see more digits down here. So sometimes that can be useful because you want more than what you need or what's given. In this one, it doesn't really matter too much because we're going to do the mean, and the rule is at least one more digit than the original data, or one more decimal place. And this is whole numbers, so we really only need to go to 35.1, and that would take care of it. So last time, it was the same thing. We had whole numbers, but I put 2 decimal places. That was because that was money, and that seemed appropriate for money to have 2 decimals go to the nearest penny. Here, this is just the number of minutes it took, and so I don't know that there's any special need to go to that extra place. It would be more accurate. It would also be a little messier, so there's just a balance there. All right, so there's our mean. And then let's calculate the median. So to do the median, we need to put the data in order, and we just did that by hand last time with 9 values that were all fairly small. Here the numbers are a little bit messier, and there's more of them. So the calculator, again, can be handy in this process. So if I hit the stat key again, and then in the edit menu, the second choice is sort A, which stands for sort ascending. Ascending meaning from small to large. So I'm going to go ahead and select that, and it wants to know what list, so I'm going to hit second and then the L1 above the 1 key again. And all it's going to say here is done, but if I go stat and edit again, then look at our list, and you now see that those values are in order. And so that's going to be useful for us in finding the median. So let's see why. When you want to do the median, you want to know where it's located. So the location of the median is 1/2 times n plus 1. Not a huge deal, but I am using a little n here because it is a sample this time. So that's 1/2 times 18 data values plus 1. That's half of 19, or 9.5. So this is a little bit confusing now because it's saying that the median is in the 9.5 data spot. And there is no 9.5 data spot. But remember our definition that if you have an even number of values, the median is in between the middle two. Well, what this is trying to tell us is that the median is in between the 9th value and the 10th values. So when I go to do that median, I want to look at my list. I want to find the 9th value and the 10th value, add them together, and divide by 2. So if I bring the calculator back in, one of the things that's nice about the way this list works is it does show you the number. So right there, that must be the 9th number, and here's the 10th number, and we put it in order, so that's important. So the 9th number in the ordered list is 36, and the 10th number in the ordered list is 37, so we would add those up and divide by 2. Numbers are nice enough I can do that in my head, so right in the middle of those, average of two numbers always takes you right to the middle, so that would be 36.5. So there's our mean, and also our median. So just a reminder what we did here, because of the 9.5, we used the 9th and the 10th data values. So we went and looked at that list and found positions 9 and 10. The median is not 9.5. The median is located between the 9th and 10th values, so we find those two and average them. All right, so we talked about shape of distributions in a graphical way in Chapter 2. And one of the things that I told you there is that if something is left skewed, what that really means is that the extremes on the left are pulling the mean to the left. And in more detail, what we would say is the mean is being pulled to the left of the median. Or if it's right skewed, the mean is being pulled to the right of the median. If it was roughly symmetric or exactly symmetric, then the mean wouldn't get pulled in any direction, or it would get pulled equally and not move, in which case these two would be the same. So here I see that they're not the same. The mean, x bar, is smaller than the median. So the mean has been pulled to the left of the median. So that implies that this is a left skewed data set. And that's kind of interesting to note because that's such a graphical idea, right? That we would look at the graph and look for tails and the imbalance in the tails. And here I haven't seen a picture yet, and still I'm making the guess that this would be left skewed because in left skewed data sets, the mean gets pulled to the left of the median and our mean is to the left of the median. The other thing that's worth a quick note is that the capital M got used for both sample and populations. So that's pretty standard to just use the same symbol both times for that. All right, let's look at some of the consequences of this being left skewed. It turns out if data was symmetric and I asked you what percentage of the data or of the students had below average time, it'd probably be a 50-50 thing, 50% below, 50% above. But because it is a left skewed data set, I would expect this to be imbalanced. So let's go count all the ones that had a below average time. So the average time was 35.1 minutes. So there's somebody that's below average. There's another, and another, and another. 35.1 is below average, just barely, but it is below average. And there's another one, and the 29. So I think that's all of them. Everything else is above 35.1. So how many did we get? 1, 2, 3, 4, 5, 6, 7. And they want a percentage, not a how many. So that would be 7 out of 18. And doing that on the calculator real quick, let's go ahead and get out of the list now. So second quit gets us out of that list area. And 7 over 18 is approximately 0.3889. That's the decimal answer. They did ask for a percentage, so move that decimal over 2 spots. And we could say 38.89% of the data set has a below average time. And again, a lot of people's initial intuition about the average is it would be a 50-50 split, but when you have a skewed data set, that's not true. And usually something's being skewed by extremes on the left, so I guess if we look at our data set, this is probably being skewed to the left by the 12-minute and the 13-minute quiz that happened. And so I think this is interesting too. If that person who took 12 minutes had taken 10 minutes, then perhaps this mean would have dropped below 35, and then these two would no longer be below average, and then it would only be 5 out of 18. So the more extreme your extremes are, the more skewed the data set can get, and the more out of balance this percentage can get. If we answer the same question with the median, it's going to be 50% each way, because you'd have these same 9, but then below 36.5, you would also pick up a couple other things. You would pick up, let's see, below 36.5, that would include this 36 and that 36. And now all of a sudden you'd have 9 values that were below and 9 values above, and it's 50-50. That's always the case for the median. That's its job. But with the mean, it can be skewed and doesn't always work out that way. All right, and then finally, let's find the mode as well. So again, the calculator is useful because the mode is the most repeated value. We could just go back up the paper and look for it there. But if we go into our stat menu and look at the list, because that list is in order, the repeats are right next to each other, and it makes it easier to find them. So let's start going repeat hunting. There's 235s, so that makes 35 a candidate for the mode. There's also 236s, so if 35 is the mode, then so is 36 because of that tie for how many times it's repeated. But never mind all that, because there's 3 people who took 41 minutes on the quiz, so that's now taken over the lead for the most repeated. Let's see if there's anything else repeated that much. And it looks like no. So the most repeated number was 41, which was repeated 3 times. So that means the mode of this data set is 41. And in a way, there's no telling where the mode is going to be. The mode, even if the data set's left skewed, it doesn't necessarily tell you. It could be to the left, it could be the right, it could be in the middle. The mode is called a measure of center, but because it's looking at repeats, and those repeats could really occur anywhere, it's hard to really judge that as a measure of center. Just more of a most common value is what we should think of it. All right, so finally, we've done all 3 of these. So suppose that a student came up to me and said, how long should I expect to take on this quiz? What should I tell them? Should I tell them 41 minutes because that's what happened to most people? Well, it didn't really happen to most people. More people had 41 than any other time, but it was still only 3 out of 18. Should I tell them the mean of 35.1 minutes? Well, that's been pulled to the left by a couple people who took it really fast. So I could do that, but it's been affected by those extremes, and I don't know if I want that. So I think the best choice would be to give them this median, because that's in the middle, and then I could tell them, well, the median is 36.5 minutes, so half the class took longer, half the class was faster, and then they can think in their own mind, like in past classes, am I usually one of the fast ones, or am I one of the slow ones? And then they'll at least know whether to expect it to be more or less than 36.5 minutes. So which of the 3 would I use? I would give them the median. And I would say a couple reasons. One, because it is not affected by those extremes. And we usually think of that as giving kind of a typical value for the data set. And then, again, the other thing that I think would be useful for them is it gives a top half and a bottom half. And people are individuals, so who knows how long it's going to take this person, but at least if I tell them that half the class is faster than that and half is slower, like I said earlier, they can think about where they normally stack up in classes they've taken before. All right, on that previous example, we talked about looking at whether data sets were left skewed, right skewed, or roughly symmetric by comparing the mean and the median. So this picture describes that using the symbol for the population mean, but it's saying if the mean is greater than the median, right? So if the mean is on the right-hand side of the median, then we would say it's been polled or skewed to the right by the extremes on that side, so that's a right skewed data set. If the mean is to the left of the median, then the mean has been pulled to the left by extremes on the left, and we refer to it as a left-skewed data set. If the mean and the median are the same, then we'd say we probably have a symmetric data set. If they're roughly the same, we'd expect it to be roughly symmetric. Now, it might turn out these would be equal and there wouldn't be a perfect mirror image, but at least the pull from the extremes is balancing out. And so in that sense, it would be at least roughly symmetric. All right, let's look at some comparisons of the different values of the measures of center, and that kind of can help us decide in later scenarios, should we use the mean, the median, or the mean. One of the things that we haven't talked about yet, but it is true about the mean, is that it's a balancing point for our data set. And what we mean for that is literally like balance. If you had a number line, let's just go ahead and put some numbering on there. Whoops. Let's do a consistent numbering. And then let's say we had 6 weights, and we went ahead and stacked those weights on the number line, and that they were all the same size weight. So we put one of them at 0, we put another one at 1, and we put one of them at 3, and then we stacked 2 of them up at 4, and one of them at 5. And then we thought, where could we put a fulcrum on this situation so that it would balance? And the claim is that the mean would be the right point. So that if we went to the calculator and added up all the positions of those weights, 0 plus 1 plus 3 plus 4 plus 4 plus 5, and divided it by the total number of weights that we placed, which was 6, when we get 2.833, the claim is then if we put a fulcrum on that number line right there at 2.833, that all of this would just balance between the left and right and it wouldn't tip off to either side. And notice that that's not trying to go to the middle weight or even in between the middle weights. These that have been set out farther to the left end up having kind of more push, torque we would say in physics, as opposed to these other ones, and it all balances out. So even though the weights aren't like split equally on the two sides, what is being split equally is the distances from that fulcrum. So if you looked at this distance to the left and this distance to the left, that should be the same as if you took the 4 distances to the right and totaled those up. So those 4 distances should equal these 2 distances, because the type of balancing that the mean does is it balances the total distances on the left and the right side. And it is affected by extreme values. And I think like looking at this balancing issue does make that fairly clear, because we should know from some experiments we've done here before that if you have things balanced and then you move this point to the left, this is going to tip this way. If you move this one to the right, it'll tip that way. So you change any of those values, it's going to affect the mean. So the mean is also known as the fair share value. And that means that it's good for taking the total and splitting it equally among all the items in the sample or the population. The mean is a good measure for data that is symmetric rather than skewed, because those extremes can really throw off the mean away from the median. But it should also be considered anytime the total is important. Even if there's extremes in the data set, if the total of all those data values is important to you, then the mean is going to be a useful tool, and we'll see that as we do homework and move through later sections. The median attempts to have half of the numbers below it and half of the numbers above it. And the word attempts is interesting. Right? You'd think you'd just say it does, but you can't always have half above and half below. Like if you have a data set with 9 items, then you can't really split that truly in half, but the median will do the best job that you can of doing a half and half split. The median doesn't balance distances. The median balances the number of data values that are on the left and right hand side. So in that group of 9, the median put 4 people above and 4 below, so that was balanced. In the class of 18, we had 9 above the median and 9 below, so it was balancing the number of data values on each side, not the distances. And it's not affected by extremes for that reason. If you move the biggest one further to the right, it's still just a big value. You move the smallest one, make it smaller, it's still just a small value. And the median is a good choice when the data set is skewed. A lot of times people don't like that one extreme could throw off their measure of center so much, so if they use the median, they don't have to worry about that. The mode only looks for common occurrences, and as we said earlier, that might not be near the center at all, so it's probably best to use the mode for categorical data. And one of the big pluses there of using the mode for categorical data is you can't average eye color, but you could say what the most common eye color was, and so the mode comes in there. So let's go ahead and look at 3 things real quick and just kind of quickly discuss through and make a pick for which measure of center we would use. So if we're looking for the monthly income by a commissioned salesperson, then what should we use, mean, median, or mode? Well, the argument I would make here is that what's probably important to this person is the total amount of money that they make during the year. So they're going to have some months that are good and some months that are bad, depending on the type of sales job that they have. But all that money is theirs, and they're willing to share from their good months to their bad months with themselves. And so the total is important in that situation, and a fair share value then makes sense. So I would go with the mean for that one. The central tendency of a class on the exam. On that exam, we're not sharing all those points. And I don't think we should worry too much as a student as to how high the highest score was or how low the lowest score was. We kind of want to know, are we in the top half or the bottom half of the class? And for something like that, the median is a better value. On the other hand, if we wanted to know the most common letter grade, then since we're talking about A's, B's, C's, D's, and F's, and just which one is most common, then we're looking for the most repeated. So now I would say the mode is the most important, or the best measure. All right, that wraps up section 3.1.